So, as a continuation from current electricity, today we are discussing only combination of resistors. And normally resistors come in two combinations. The first is called series, and let's start by discussing that. Series occurs when resistors are joined end to end. Let me explain what that means. You can see the standard symbology, I'm sure you learned that. This is my cell and these are my two resistors. When they're joined end to end, you can see one end of the resistor and the other end are joined in one line. When I show you parallel, you will be able to see the clear difference between the two combinations. So let's call this one R1 and let's call this R2 to denote my two resistors, and this is what you call a typical series combination. That is, these two resistors are joined end to end with this battery, and this is your circuit diagram. Now if you see the current that is drawn from the cell, it will come out from the positive end always, and the current moves throughout the circuit, and you can see that the same current is flowing through both the resistors. You need to follow the wire, the current goes along this wire, and you can see that the same current, let's call that current I, goes through the two resistors. So between the two resistors the current is constant. Now we know Ohm's law, and we know that V is equal to IR. So let's keep that in mind. Now if V is equal to IR, I is a constant, our R's are changing as R1 and R2, then it's pretty clear that V, which is potential, changes, but I, which is current, is constant. So now if V changes, what is V net? Okay, it is the sum of the individual potentials across each resistors. Let's call V1 the potential between resistor R1 and V2 the potential difference between resistor R2. So now when we have V net is equal to V1 plus V2, let's substitute V is equal to IR, going back to Ohm's law. And when we do this substitution and we know that I is constant, we will get IR net is equal to IR1 plus IR2. What is IR1 and IR2? It is simply the potential difference across the ends of this resistor. And using Ohm's law, we know that potential difference is equal to current into resistance of that resistor. And so in this combination, it's called a series combination, if we take I common, we get a very simple formula which we can use for all series combination. That is, you simply add up the resistors when they are in series. And so moving on, this is your series resistors. But moving on, let's see what other combinations we have. We have our second combination called parallel resistors, and parallel is a very typical case, as I'm going to explain to you. It involves the use of a junction. These are your two resistors in a typical parallel circuit. That's your cell. Let's label this as R1 and label this as R2. Let's put down Ohm's law by the side. We're going to use this in all cases, right? Now in the series formula, what we did was we traced the path of the current to find out whether the current is constant or it changes. So here let's do the same. Let's trace out the path of the current. So the current is moving along the circuit from the positive terminal to the negative terminal, but when it comes to this point is what you call a junction, and the current can move in two directions, and it does. So the current splits up, and the way in which the current splits up, it's always in ratio of these resistors R1 and R2. However, you will learn this later in grade 12 under Kirchhoff's law when you study how current splits up. But let's look at the very simple 10th grade scenario. The current is splitting up, so very simply I changes. But I is changing in ratio of the resistance. So if R1 is a big resistor in comparison to R2, the current going to R1 will be less than the current going to R2. So effectively, when you have the product of I and R, potential difference, which is the product of I and R, remains constant, because you'll have a small current for a large resistor and you'll have a large current for a small resistor, as you can see in this. Now let's continue tracing the path of the current. The current continues moving. Now at this junction, once again the two currents meet, and when they meet, they produce the third current, a single current which flows back to the negative terminal. So this is how your circuit works in a parallel resistor. So your formula now is I net is equal to I1 plus I2, and let's say I1 is the one going to R1 and I2 is the current going to R2. So now using Ohm's law, we know that I, which is current, is V by R. So let's take V by R net. Note here that V is constant. I've already shown you V is constant. So we're not going to have different V's in each formula. V remains the same throughout. However, your resistors are different. So now if you are cancelling V throughout our equation, that is your derivation of how to get a net resistance in a parallel circuit. And you will use this formula to solve all your questions. Just remember that R net is in the reciprocal. So once you solve your right hand side of the equation, you must reciprocate it to get the correct answer. And I see most students who forget to do this. So having learned how the resistances are calculated in these two circuits, let's look at complicated circuits. Let's look at circuits where series and parallel come together. So my first question, this is still an easier one, the next one will be harder, is this. We have this first resistor, we have a second resistor, we have third resistor here. And let's see how this circuit can work. Let's label this R1 and let's call this 4 ohms, R2 2 ohms, R3 6 ohms. So if we see the current, we can always make out parallels with tracing the path of current. The current comes, we have a junction, the current splits up into two. I've already told you, and the junction will split up into how many ever parts of the junction there are, and the current will move here. Now the current going through R1 and R2 is the same. You can see that. See, the current, this bit that has split up before, is the same going through R1 and R2. So R1 and R2 are obviously in series. So RS, which is the net resistance of the series, is simply R1 plus R2, which is 4 plus 2 ohms, which gives us 6 ohms net. And R3 gets this different current which flows through this, and these two currents finally meet, they come out of the junction and they flow back to the negative terminal. So now we can see that since we have the net of R1 and R2, the net resistance is RS, which is 6 ohms. So now to further solve this circuit, it becomes clear that RS and R3 are in parallel. So now to solve this bit, what we need to do is take 1 by R net, which is the final value we want to find, and put in 1 by RS plus 1 by R3, which is, both are 6 ohms, so it's easy for us to solve. 1 by 6 plus 1 by 6. When you take LCM, you get 2 by 6, which is 1 by 3. Now the answer is not 1 by 3. I told you this is in the reciprocal, so you need to bring this up. So final answer, R net is equal to 3 ohms. What we have done is we have reciprocated this. R net goes to the top, so even 3 goes to the top, and this is your final answer. Further, we're going to look at an even more complicated circuit, and let's see how we can solve that. Here we're not given any cell, we're simply given terminals. But do not be afraid of terminals. Terminals simply indicate the flow of current, which is what a cell does. A cell provides current. So effectively, if you're given terminals A and B, you can just take current from any one of these ends and assuming it flowing throughout this thing. So let's label each resistor R1, let's say it's 10 ohms. Let's label R2 as 5 ohms. Let's label R3 is equal to 3 ohms and R4 is equal to 2 ohms. Do not be afraid by these terminals A and B. Just take current coming from A, for example. Now this is your junction, so split it into 2. So now this is clear that whenever the junction comes, there is some form of parallel in this circuit. So now this current, the one going to R1, is going to come all the way here, and the current that goes through R2 goes down here. Just follow my cursor. Goes through R3, goes through R4. Now the current going through R2, R3 and R4 is the same. So these are in series because there is no junctions, one direct line. The resistors, that I told you before, are joined end to end. So that is your series. So let's trace the path of the current. Now these two currents meet at this second junction and they flow through into B. So where are your series and where are your parallel? Let's take RS, net of the series circuits, and it is simply R2 plus R3 plus R4. Why is that? I showed you how the current that splits up over here is the same that goes through R2, R3 and R4 if you follow my cursor. But over here it's a junction, so the current splitting into R1 is different from the ones flowing through R2, R3 and R4. So R2, R3 and R4 are in series, which is your net series, which is 5 plus 3 plus 2, which is equal to 10 ohms. And your R1 is in parallel with all three of them. How do you solve it? So you take RS, which is your net of all three of them, and you write that RS and R1 are in parallel. Now if you want to solve them, you want to find the net, just use the formula that I've proven to you before. Take 1 by R net equal to 1 by RS plus 1 by R1, which gives you 1 by R net is equal to 1 by 10 plus 1 by 10, which is equal to 2 by 10, right, which is equal to 1 by 5. If we cut 2 and 10, we get 5. Now you remember, this is not your answer, you need to reciprocate it. So on reciprocating it, you get R net is equal to 5 ohms. And that is your answer. And this is how you would solve complicated circuits that include both series and parallel. Thank you.